What's poppin', ne'er-do-wells? Today, we are going to talk about your favorite thing, math. And you're going to say, but Mr. Barton, that sounds like a setup. That sounds like something that's not my favorite thing. And it's okay, kids. You don't have to lie to yourselves and say you don't like math. I won't tell your parents. But we're going to talk about coloring. We're going to talk about nth root operations. And you're going to say, what's an nth root? Well, n is just like the generic letter we use in math for like any integer that you care about, right? It could be 8, it could be -4, it could be 13 and a half. No, not and a half, right? It has to be a whole nice round integer number. But we're going to talk about roots and how to simplify them. You're going to have to do a little bit of numerical factoring, a little bit of division with remainders. But I think you'll live. You might not. So you might want to go hug your mom, dad, aunt, uncle, grandma, grandpa, whoever it is you live with. Send your best friend a text. Tell your boyfriend and girlfriend, hey, you know what? If I don't come back, you can have my Animal Crossing game. Tell your little brother where you hide your holographic Charizard. That way, he can have that when you don't come back. All right, let's get into math. Let's skip that slide. All right, let's talk about what everything is called before we get too gung-ho about this nonsense. So, this thing, the little number that goes on the root, right? We've seen things like this, cube roots. That number is called the index. I will sometimes call this the root number. I think the index is the more kind of technical word for it, but you're gonna have to forgive me. I've gotta say words that mean stuff to you, but it's called the index. All right, the stuff inside the radical. So we're talking about this x and this m thing. Everything in the radical, the whole thing together, is called the radicand. This particular radicand has a couple of components to it. The thing that has the power on it is called a base. So if we have like 3 to the second power, 3 is the base. And then, of course, the exponent, another word for exponent, is power. And then this thing is just the radical sign, right? That means we're doing some variation of a root that you guys are familiar with. So let's go ahead and take a peek at some of these practice problems. So let's read the instructions at the top. It says, when reducing square roots, we need a pair. Pair, the word pair means 2. You need 2 of the thing of the same number variable. So what we're going to do here is we're going to factor these things as much as we can, and then we are going to make groups of 2 matching things, and then we'll move them outside the radical. So let's look at 24 first. Let's factor 24. And I like to make a little factor tree. This is kind of like those times when you were in like 3rd, 4th grade, you were learning your times tables and your factor families, if you recall. Ooh, that's a deep memory, huh? And then right around the winter holiday season, your teacher said, we're going to do a project, right? They came in one day looking a little tired, a little haggard, their hair not quite done right, their shoes mismatched. They'd clearly been out a little late last night, and they're like, hey, kids, don't talk so loud, keep it down. Mrs. Martini had a few too many Smiths last night. You feel what I mean? So she said, we're going to make a factor tree. And she'd give you a big number, right? Like 80. And you'd have to factor this thing. You'd be like, all right, 2 and 40. And then how about 20 and 2? And then how about 2 and 10, right? And you'd make one of these, and then you'd slap some green on it, right? And then you put like a little star on the top. And then you put some little jingle bells on the side. And then next thing you know, your parents are coming in for meet the teacher night on the day before winter break, and they're like, "Look what little Jimmy made! Beautiful factor tree." And then you spent like a week on this thing, and the teacher was like, "Hey, keep up the hard work, kids." We're gonna do that. So I did an example, but let's look at 24. So we're gonna factor this. We need to ask ourselves, what two things can I multiply together to get 24? You can start with the easy one, of course. You can do 2 and 12. If you chose 4 and 6, though, that's also okay. The order doesn't matter. You can factor it anyway, as long as they do actually multiply correctly. All right, 2 is a prime number, so that one's stuck there. Because if we try and keep factoring 2, we get 1 and 2. Oh, and then we get 1 and 2. Oh, and then we get 1 and 2. And then it just goes on forever. So once you hit a prime number, you just stop. All right, 12 is 2 and 6, and then 6 is 2 and 3. Okay, this is factored because 2 and 3 are prime numbers. So all the things at the bottom of our branches of our factor tree are prime, and we can't factor anymore. Now what we need to do is make pairs of numbers. And we're only looking at the ones at the bottom. So ignore the 24, ignore the 12, ignore the 6. Well, I have a pair of 2s right here. Can I make another pair? No. These don't match, so they're stuck unpaired. So what happens is the pair gets to go outside the radical. And even though there's 2 2s here, you only write the number one time for each pair. So one pair of 2s, we have 1 2 on the outside. Okay, so we're going to have a 2 on the outside of the radical. These things are kind of like kids around homecoming or prom time. And they really wanted to go to prom or homecoming. And they asked out this boy or girl that they really had a crush on. And that boy or girl's like, "Ew, you play Fortnite? Ugh, I only hang out with cool kids who play Minecraft. I'm not going to homecoming with you." So this 2 and 3 couldn't get a date because they don't play the right video games. So they had to stay at home inside the radical. So we have a 2 inside the radical, we have a 3 inside the radical, and we multiply them back together. So the 2 stays out there, and then 2 times 3 is 6. So radical 24 simplifies to 2 radical 6. All right, let's do another one, maybe without quite so many metaphors and stories so that we get the idea. So we'll factor this. How about 4 and 20? All right, 2 and 2. How about 2 and 10? And then 2 and 5. All right. So I've got a pair of 2s. I've got another pair of 2s. And then I have a lonesome 5 who couldn't get a date to homecoming. So this pair of 2s goes outside the radical. This pair of 2s also goes outside the radical, and we multiply all the pairs together. Inside the radical, this 5 has no date, so it stays inside. Multiply the outside, multiply the inside if you have to, like we did over here. 2 times 2 is 4, radical 5. That's our answer. The square root of 80 equals 4 radical 5, and this is the reduced form, or the simplified form. Okay. So now, let's look at x to the 16th power. I'm going to do this the hard way, and then I'll show you the trick to it. Okay. So what two things can we multiply to get x to the 16th? We're going to have to remember our exponent rules that we learned last unit, I think. So we've got x to the 8th times x to the 8th, right? Because if I multiply these, we add the exponents. 8 plus 8 is 16. All right, we could do x to the 4th and x to the 4th. We could do x to the 4th and x to the 4th here. And then we can do x squared, x squared, x squared, x squared, more x squareds, and you kind of get the idea where this is going, right? And then all of these can be broken up into x's. So we're going to have, you guessed it, 16 x's. And you're going to have to wait while I fill them all in. But we got a lot of them. Ooh, we're losing track here. I think 2 more. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Get rid of this extra line. Okay, so then you start pairing these bad chickens up. We've got 1, 2, 3, 4, 5, 6, 7, ocho pairs. So all of these pairs go outside the radical. So we've got x times x times x times x times x 8 times 1, 2, 3, 4, 5, 6, 7, ocho. And then nothing left inside because they're all paired up. Everyone gets to go to prom this time. So x times itself 8 times is x to the 8th. And you're going to say, Mr. Barton, that's a lot of work. Is there not a faster way to do that? Well, the rule for it is as follows. For variables with exponents inside radicals, we have to look at the index. And you're going to say, Mr. Barton, there is no index. There's no number there. If there isn't an index for a radical, the invisible index is a 1. No, that's exponents and coefficients. It's a 2. Okay. So all you have to do to simplify this the fast way is you divide the exponent of the variable by the index. So 16 divided by 2 is 8. So you're going to have x to the power of 8 outside. Let's look and see what happens if it doesn't go in evenly. So 2 goes into 7. All right, we got to think back to, what is it, like kindergarten? We take 7, we divide by 2. 2 goes into 7 3 times. 3 times 2 is 6. Subtract 1. 2 doesn't go into 1, so we have a remainder of 1. So these 3 mean we're going to have 3 pairs of x's. And then this remainder of 1 means we're going to have 1 left over x. So we're going to have x to the 3rd radical, put the remainders inside, and the exponent on the remainders is whatever the remainder is, 1. And there we go. Not too bad. All right, let's look at these. These ones are a little bit more complicated. So what we're going to do is we're going to first fill in our index. It's the invisible 2. We're going to factor the number and then divide the exponents on the variables. So for 45, we have 9 and 5. 9 is 3 and 3. And then 3, 3, and 5 are all prime numbers. So we have a pair of 3s. Those get to come outside the radical. I'm going to leave some space for the variables. The 5 couldn't get a date to homecoming, so it stays inside its house, inside the radical. Now we divide the exponents on our variables for the shortcut. So 2 goes into 2, 1 time. 2 goes into 14, 7 times. 2 goes into 6, 3 times. And none of them have remainders. So this is our answer. All right, let's talk about what happens if our exponent is not a 2. Or not our exponent, pardon me, I misspoke. Our index. If we are going to follow the same procedure, let's factor this 8. So 8 is 2 and 4. And then 4 is 2 and 2. We're actually not always trying to make pairs. We're trying to make groups of whatever size the index is. So if our index is 3, we want a group of 3 matching numbers. If it was 4, we'd want a group of 4 matching numbers. So if we look at 8, we can make a group of 2s because we have 3 of them. So this group gets to go outside, and then there's no leftover numbers. Everyone, this is like a group of 3 best friends who kind of just agree that they're all each other's dates to homecoming, right? So nothing is left inside, the 2 comes outside the radical. Then the division property for variables with exponents still works. So 3 goes into 3 1 time. 3 goes into 9 3 times. There are no remainders, So the radical is empty and we don't need to put it. So our answer is 2xy to the third. All right, let's do 2 more. Ooh, a 4. All right, we're going to see some remainders. We're going to see some fancy stuff here. So let's go ahead and factor our 32. This is 4 times 8. And then this is 2 times 2. This is 2 and 4. And then this is 2 and 2. So we can make a group. We're looking for a group of 4 because that's our index. So we have 1, 2, 3, 4 2's. So we get to take a 2 outside the radical. This 2 didn't get invited because that 2 likes the wrong video games. So that 2 stays at home inside here. Now we start dividing and we're going to have to look at some remainders. So 4 goes into 10 2 times. So we have x squared outside, but not exactly 2 times. 2 times 4 is 8. So 8 of these get put into groups. The other 2 didn't get a date and have to stay inside. So 4 goes into 10 2 times with a remainder of 2. So we have x squared inside. 4 goes into 30. Let's maybe write this one out. 4 goes into 30 7 times, I believe. 7 times 4 is 28. Subtract 2. We have a remainder of 2. So we're going to have y to the 7th on the outside because it goes in 7 times. And then our remainder goes inside. Y to the power of 2 for our remainder. 4 doesn't go into 2, so there are no groups. These 2 are stuck inside because there aren't enough to even make one group. So this is our answer. All right. Let's go ahead and look at the 5th root of 243, a to the 20th, b to the 25th. This 243, let's see what goes into this. I have a sneaking suspicion it's 3. I think it is 3. Let me just double check with my mental arithmetic. This is 3 times 81. All right, 81 is 9 times 9. And then 9 is 3 times 3. So we try and make a group of matching numbers. We have 1, 2, 3, 4, 5 3's. So we make a group of 3's. They come outside the radical. Nothing is left over. All of it got factored out. 5 goes into 24 times. So we have a to the 4th. 5 goes into 25 5 times. B to the 5th. And there are no remainders, so there's nothing inside the radical. So the radical goes away, and our answer is 3, a to the 4th, b to the 5th. Not too bad. All right. Let's talk about how we do operations with radicals if we're adding and subtracting. Adding and subtracting have the same rules. They're basically the same operation. So only like terms can be added or subtracted. So what we mean by like terms for radicals is they have to have like radicals. So if you have 2 radical 3, you have 2 radical 3's plus 4 radical 3. These are like terms because their radicals match. So this would be 2 plus 4 is 6 radical 3's. You kind of think of them like variables, like x's. 2x plus 4x is 6x. 2 radical 3 plus 4 radical 3 is 6 radical 3. It's probably necessary to simplify some problems. You're going to have a radical 32, and then you're going to have to add it to something with a radical 2, and you're going to say they're different. You might have to simplify first before you're allowed to add or subtract. So let's try some. All right. We have 4 radical 3 plus 4 cube root of 3. This radical and this radical are not the same. This one has an index of 2, and this one has an index of 3. So because the radicals don't match, we can't add these. So this is the answer. It's not addable because our radicals are different. All right. Radical 18 plus radical 50. You're going to say, whoop, Mr. Barton, can't add those either. They're different. But we have to try and simplify first. So 18 is 9 times 2, and then 9 is 3 times 3. So our index is an invisible 2 for both of these. So we have a pair of 3s, they go outside, and a radical 2 because the 2 doesn't have anything to pair up with, so it stays inside the radical. Plus 50 is 25 times 2, and 25 is 5 times 5. So we have a pair of 5s that get to come outside the radical. Then the 2 stays inside. And look, matching radicals. So 3 plus 5 is 8, and then we keep the radical the same. All right. Now we look at this one. We have to try and simplify. So we're going to factor 16. This is 4 and 4. This is 2, 2, 2, and 2. So we make a group of 3 numbers. So 2 comes outside. Cube root, we have to keep the radical the same. If this was a cube root, this is a cube root also. The 2 that didn't get a partner stays inside. Factor 250. This is 25 times 10. This is 5 times 5 and 5 times 2. So we make a pair of 5s. So minus, because we have a minus right there, 5 cube root of 2. And then this one's already simplified. We can't factor 2. It's just 2 and 1. So you see how that's an eraser and this is not erasing, right? You see that? That's incredible. So we just bring this one down. Why does it look like an eraser now? I want it to look like a pen. This program's whack. Cube root of 2. Now we just combine like terms. So 2 minus 5 is negative 3, plus 7 is 4. Bring down your radical, cube root of 2. All right, there's adding and subtracting. Let's talk about multiplying. We're not going to do dividing, I don't think. Dividing, like most things in life, is a little hard. So we'll probably save that for later, but maybe not. All right, so here's the rule. We're going to FOIL, aka distribute. You multiply the outside numbers, and then you multiply the numbers underneath the radical. Okay. Technically, the radical or the root numbers have to match. You can't multiply square roots to cube roots. That's a little bit different. But I don't think we're going to have to worry about that. So, looking at this first easy example, we're going to multiply the coefficients together. So 5 times 4 is 20. Then we multiply the radicals together. Radical 3 times radical 2 is radical. 3 times 2 is 6. At this point, we need to check something, though. We need to check to make sure our radical is simplified. This is just 2 and 3. I can't make any pairs, so that's as simplified as that can get, and this is our answer. All right, here we have 2 radical 3 times 4 plus 4 radical 5. So we're going to take this and distribute it into both of these terms. So 2 radical 3 times 4. We multiply the numbers outside radicals. 2 times 4 is 8. Then this radical 3 doesn't have a radical to multiply with, so we just bring it down. Now we distribute to the 4 radical 5. 2 times 4 is 8. And then radical 3 times radical 5 is radical 15. And then this is just 3 and 5, so we can't simplify. So our answer is 8 radical 3 plus 8 radical 15. Let's look at maybe a couple harder ones. Here, we have a binomial. We have 1, 2 terms, 1, 2 terms. So we're going to have to FOIL or distribute. So we're going to do 3 times 4, then 3 times radical 6, then 2 radical 5 times 4, then 2 radical 5 times 6. So let's start with the 3. 3 times 4 is 12. The invisible coefficient here is a 1. So 3 times 1 is 3. Bring down your radical 6. We're done with the 3. Now we're on 2 radical 5. 2 times 4 is 8. Radical 5 doesn't have anything to multiply to, so we bring it down. So this is radical 5. Sorry, I had to think there. I had a little brain fart. Then 2 times 1 is 2. Radical 5 times radical 6 is radical 30. All right, now we just check. Do we have any like terms? No radicals, radical 6s, radical 5s, radical 30s, no. Can I simplify the radical 30? 5 and 6, 2 and 3. Nope, it doesn't simplify. I can't make any pairs. So this is our answer. All right. Now, let's look at this one. Sometimes kids get confused about this just because they're like, what's squared mean? Do I just square them? No, we don't distribute because we have this plus in the middle. What we want to do is write this twice and then distribute. So we're going to have 3 plus radical 5 times 3 plus radical 5. So 3 times 3 is 9. Plus 3 times radical 5 is 3 radical 5. Radical 5 times 3 is 3 radical 5. And then radical 5 times radical 5 is radical 25. Now we simplify. 3 radical 5 plus 3 radical 5. They're both radical 5s. So we can add the coefficients. This will be 6 radical 5. And then radical 25. Before you factor, think about it. Do you know the square root of 25? Yeah, Mr. Barton, of course. That's easy. Yeah, thank goodness. It's a 5. So you don't always have to do the factoring. If you know the square root, just do the square root. Square root of 25 is 5. Plus 9. 5 plus 9. These are like terms because they don't have radicals. So 5 plus 9 is 14. Plus 6, radical 5. And this is our answer. All right. That is it. You are done. Big smiley face. That's actually a doo-doo smiley face. What do smiley faces actually look like? What if we like... do it like this. Put some eyes on that dude. Put like a big old schnoz on him. What else do we want? Can I get rid of these lines now? No, this is all one thing. It's not all one thing. I unthinged it. Get rid of that. Get rid of that. What else does he need? Maybe it's a lady. Maybe it's a lady. How about heart and then maybe it's an ugly lady. And every lady's got to have bangs. And then some like big old lips. She's looking cute, isn't she? All right. Before you guys get too excited, you are done with your notes. Congratulations, you lived. Go ahead, hop back in the WebEx. Let me know if you have any questions. Start working on your homework. And if you get stuck, let me know. Have a great day, ladies and gentlemen.